This is a quick video to highlight how to construct the Taylor polynomial and ultimate infinite Taylor series for the function cosine of x. So we start with, let's approximate the cosine of x to just be a constant, c sub 0. And as we do, we're going to center this at x equals 0. So what we would say is the cosine of 0 is equal to c sub 0. The cosine of 0 is equal to 1, and so c0 is equal to 1. So what we're saying is that the function cosine of x can be approximated by the function y equals 1. And you can see that that's actually accurate on occasion. Every 2 pi. Like negative 2 pi we're right on, at 0, at 2 pi, and at all increments of 2 pi we would be spot on. But of course we don't want to leave it at that, we want to do better. And so what we say is, let's approximate the cosine of x function to be a linear function. C sub 0 plus the slope times x. Now we use c sub 0, these subscripted c values as our constants instead of like, the good old mx plus b from your algebra days. Now, what you have learned, I hope, is that once a constant is established, we don't have to keep recomputing it. We know that c sub 0 is going to come out to 1 every single time. But now we want to figure out that slope. And so we think about slope as in the derivative, and we take the derivative of cosine and get negative sine. We take the derivative of this linear function over here, and of course the derivative is the slope, so we just get c1. And since we're centering at 0, we compute what happens to c1 when x equals 0. Well, the sine of 0 is 0, and so c1 is 0. And we just keep up this process. We keep adding terms to our polynomial. Like, let's go quadratic now. When we go quadratic, we'll add a new constant or coefficient, and we'll add that quadratic term. Now, as I said, once we get the coefficients, we don't have to recompute them every time. So we know, I should really be using approximately equals here. We know that c0 is going to be 1. We know c1 is going to be 0. And we want to figure out c2. Now, as we stage through this, each time we're going to take repeated derivatives. So we've done no derivatives to get c0. We've done one derivative to get c1. We're now going to take two derivatives. The derivative of cosine is negative sine. The derivative of negative sine would take us back to, well, not back to, but take us to negative cosine. And over here, the first derivative of a constant will be 0. The derivative of a linear term, I know it's 0, so it's kind of a moot point anyway, but yet the derivative of a linear function is constant. The derivative of a constant is 0. So really all that's going to matter is the derivative of this quadratic term. So the 2 comes out front, decreased by 1. We would get, let me just write that down kind of as a note over here. The first derivative would be 2c2 times x. And then if we took the derivative of that linear term, we would just be left with 2c2. And as always, we're centering this at 0. As always in this case, I mean. We're centering at 0. And so we would get negative 1. Cosine of 0 is 1, so negative 1 is equal to 2c2. Divide both sides, and we get c2 to be a half. Now notice what I'm computing here are these coefficients. We've got a 1 for that coefficient, a 0 for that coefficient, and now a negative 1/2 for that coefficient. And let me just show you that this is actually true. A negative 1/2 x squared. Yeah, we see that blue parabola is starting to model that cosine wave a little bit better than just that horizontal line did. Let's keep going and see how much better we can do. So the next move would be to go cubic. So we'd have a coefficient constant. We'd have a coefficient on the linear term. We'd have a coefficient on the quadratic term. and then we'd have our coefficient on our cubic term. Now again, C0 is 1, C1 is 0, C2 is -1/2, C3. To get C3, we're going to work on a third derivative. Now the derivative of cosine is negative sine. There's one derivative. The derivative of negative sine is negative cosine, as we saw here. That's two derivatives. And the derivative of negative cosine is going to be positive sine, because the derivative of cosine is negative sine, so we get the double negative going there. So we'll be back to sine. Now here's the thing. I'm not even going to worry about this side, because the derivative of sine of, the evaluating at x equals 0, this third derivative, the sine of 0 is 0. And so whatever happens over here, when we solve for that coefficient, of course it's going to come out to be 0, because 0 times x cubed is going to be 0. And so we start to see a pattern, which is really important in this whole construction process. And the pattern is this. This term was meaningful, we got a 1, then we got a 0. This term was meaningful, we got a -1/2, then we get a 0. Do you see how every other term is going to come out to be 0 because of the way derivatives work with sines and cosines? Every other derivative is going to have a sign, and the derivative evaluated at 0, the sine of 0 is going to be 0, and so every other term is going to be 0. So let's now focus on just the terms that are going to be non-zero. All right, well the next one should be non-zero, so we're going to go quartic next. Quartic is a 4th degree polynomial, and here we go. All right, a 4th degree polynomial, so we need 4 derivatives. The derivative of cosine, negative sine. The derivative of negative sine, negative cosine. The derivative of negative cosine, sine. And the derivative of sine right back to cosine. We made it back to cosine of x on that 4th derivative. Now, as you take derivatives, the derivative of a constant term is 0. When you take the second derivative of this linear term, it'll go to 0. When you take the third derivative of this quadratic term, it'll go to 0. And when you take the 4th derivative of this cubic term, it'll go to 0. The only thing that's going to really matter here is what happens on that last term. Let's run it through it quickly. The first derivative will be 4c4x cubed, the power rule. Take the derivative again, we'll get 12c4x squared. And then we'll get 24c4x, that's 3. And then one more derivative, we'll just have 24c4. So the 4th derivative and the 4th derivative. At 0, well, the cosine of 0 is 1. And so now we've got 1/24. So again, remember, these are the coefficients. So we have a coefficient of 1 and then a 0. And then a coefficient of -1/2 and then a 0. And then a coefficient of 1/24. Let's stick those into Desmos and see. And what I'm going to do now is acknowledge that a 0x or a 0 x squared doesn't really help with anything. So I'm only going to focus on the non-zero terms. The next one was 1/24 x to the 4th. Ah, look at that. It's starting to wiggle its way and follow that cosine curve a little bit more closely. But as all polynomials do, especially even polynomials, both ends are going to either both go up forever or both go down forever after some of the wiggling, after some of the ups and downs happen. So we just have to keep working our process. Now another thing you might notice here is that the signs alternate. We have a positive term, then a negative term, then a positive term, and the next one's going to be a negative term. And not a 5th degree, that's going to be a 0. We're going to go to a 6th degree. And let's see if you see a pattern here. The exponent of 2, if you take the factorial of it, like 2 factorial, of course, is 2. If you took the exponent of 4 in this case, 4 factorial is 24. And so just to help you see it, I'm going to put this in terms of factorials. the denominator of our fractions is always the same as the exponent factorial. 4 factorial, 4 times 3 times 2 times 1 is 24. 2 factorial. Even on this one, you could think of it as 1 over 0 factorial, because 0 factorial is 1. Go back to the module and you'll see why. So 0 factorial, 2 factorial, 4 factorial, I hope you now see a pattern. The next term is going to be 1 over 6 factorial, x to the 6th. And then the next term is going to be 1 over 8 factorial, x to the 8th. And do you see that as I keep going, minus 1 over 10 factorial, x to the 10th. As we keep going, this polynomial approximates that sine wave better and better and better. All right, let me go back to my document, because now I hope you can generalize what's happening here. What we're saying is that the cosine of x is approximated by, we had 1 over 0 factorial, and then it was minus 1 over 2 factorial x squared, and then it was plus 1 over 4 factorial x to the 4th, and then 1 over 6 factorial x to the 6th, and then 1 over 8 factorial x to the 8th, and then I'll do one more since I have the room. All right, that's the polynomial. Now this thing would just go on and on. Let me put a little dot, dot, dot. That thing, we could go on and on and on and on forever and ever and ever and ever. The more terms we have, the better the approximation. All right, now to help write this as a formula, I'd like you to consider counting at n equals 0, and then we would have n equals 1, and then we would have n equals 2, n equals 3, n equals 4, n equals 5. Here's what we do with sequences and series. We take each term or each item in the series and we give it a subscript or a classifications here, starting counting at either 1 or 0. I hope you saw from the modules we can start counting at 0. You can start counting at 1. I think it's useful to start counting at 0 in this case. And if we start counting at 0, what we want to do is express what we see here in terms of a formula. We're summing up as n goes from 0 in my case to 1 to 2 to 3 to 4 to 5 to 6, ultimately to infinity. And what I see here is 1 over. Every time I have 1 over, 1 over, 1 over, 1 over. 1 over what though? Well, when n is 0, we get 0. When n is 1, we have a 2 factorial. 2, 4 factorial. 3, 6, 4, 8, 5, 10. Do you see the pattern? Whatever n is, the denominator is twice that factorial. So twice 2 is 4, twice 3 is 6, twice 4 is 8, twice 5 is 10. The denominator is always twice whatever n is factorial. And then that gets multiplied by x raised to the power of that same thing. When n is 1, we have a power of 2. 2, 4, 3, 6, 4, 8. It's always to the power of 2 times n. And then, hope you saw from the module, to get this alternating idea, alternating signs, positive, negative, we're going to multiply by -1 to a power. Now, you guys, honestly, this is just something I have to think about every single time. Maybe you do, maybe you don't. I usually just start by thinking, what if I did -1 to the n? So let's start here. When n is 2, -1 squared, -1 times -1 is +1. That's going to make everything positive. Good. When n is 3, -1 cubed would be -1, making everything negative, which is good. And so -1 to the n, as n varies, is going to give the right sign, the positive or the negative as it should be. So what we're saying is I can now take that away and call it an equal sign, because I'm saying that if n is allowed to go to infinity, in theory, then the cosine of x is the sum, as n goes from 0 to infinity, of 1 over 2n factorial times x to the 2n and then alternate those signs, -1 to the n. Now you can see it in Desmos. Come on. If you're wondering what's going on, I put my pen on my tablet, which made my mouse be wonky, and so things were crazy here. Okay, so if I say y equals sum, then that's how Desmos knows exactly what you want to do. And now Desmos, I can't put the infinity in, but I can say n goes from 0 to a. Doesn't matter what letter you put up there, I'll just do a. And then 1 over, and it was 2n factorial. It was x to the 2n. And then don't forget the alternating sign of -1 to the n. Make a slider for a, absolutely. Let's let a go from 0, and I'll just go to 50. You'll see the point if I let a just go from 0 to 50. Let me turn that one off. Let me make that one not black. Hopefully you can see it well. I'll make it orange. And I'll make it like this, so hopefully everything will be clear. Are you ready? So as we go from 0 to 1 to 2 to 3 to 4 to 5 to 6 all the way up to 50, watch what happens. Look at that. Now eventually that polynomial takes off in both directions on the ends, but the more terms you have, the more the polynomial mimics that cosine curve. Now, even with Desmos, it gets a little bit wonky here because we're talking about, like now, a is 45, so n is 0 to 45. So like a 2 times 45 is 90, and 90 factorial. 90 times 89 times 88 times 87. It gets a little out of control even for Desmos to keep up with the computations. But by the time we get to 50, we can see that at least in this viewing window, it'll take a second to catch up here. At least in this viewing window, that polynomial is mimicking that cosine curve for quite a while. Now, 50 is not even close to infinity. Imagine, theoretically, imagine just growing this thing off to infinity. We would have a way to express the cosine of x as a polynomial. Crazy.